Okay, so we're looking at this. Can anyone tell me what it looks like? What kind of graph is it? No. All I heard was Cartesian, so if you said something other than Cartesian, I didn't hear you. So, what kind of graph is it? Y equals X. I'll give you a hint. Oh, good, it's linear. Yeah? Right? It says linear on there 3 times, including the heading. What's it look like? Someone tell me. Seriously? No one? Yeah, what does it look like? You're supposed to graph it on there. It's a line, yep. Be more specific.
2 lines, line A.
No. All right, so we're all sitting here going, oh my goodness, I don't know how to do this and I should. I'm saying the I should part, you're not, right? So you're sitting there and I've given you an equation, y equals x. It's a line, so how many points do I need in order to draw a line? 2. So do you reckon I could make up a couple of points? So for example, I could try x equals 1 and x equals -1 and work out the y values and then join them up. Do you reckon I could do that? Yes, you could. Right? So when x equals 1, what does y equal? Nope. The equation is y equals x. So if x is 1, what's y equal? 1. It's not a hard question. So where is that point on my graph? There? Is that 1, 1? Yeah? So when x is -1, what's y equal to? -1. You reckon you could graph that point? Oh, it's not very straight. Sorry, let me just... I hate it when it does that. Let's try it this way. Nope, do it again. Let's just leave it because I don't want to keep rubbing it out. Okay, so I was to join that up now. Ooh. There's my line. Okay, so if you're unsure, you can always just pick a few points and work it out, particularly for linear. Okay, really crying right now. Okay, I'm going to come back to this in a second because we literally did a term of graphing a linear equation last term. Didn't we? Yeah, last term. All right, so can I remember what the gradient intercept form of a linear function is? mx plus c. Does that sound familiar? Yes? Thank God. What does the c represent? The y-intercept. So if I go back up to my equation I asked you to draw a moment ago, y equals x, what's the y-intercept? 0. Ding, 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 ding. Right? If I go back to that equation, y equals mx plus c, what does the m represent? Gradient. Right, what's the formula for gradient? Rise over run. What's the big kid formula for gradient? Yep, good. y2 take y1 over x2 take x1. What's the shorthand version of that? Do you remember?
Triangle.
Yeah, triangle. Difference in, yep, all of those. Does anyone know what the triangle is called? Delta. Right, so that's the big kid version of gradient. Little kid version of gradient is rise over run. Whatever works for you. Okay? Now, if I go back to this equation, what's my gradient? This equation, what's my gradient? 1. Where does the gradient appear in the equation? Before the x. What do we call the number before the x? Coefficient, thank you. It's the coefficient. So if we have y equals x, the coefficient of x is 1, which means my gradient is 1, which means if I put it in terms of rise over run, it's going to be 1 over 1. So when I start with my y-intercept, which I've already identified as 0, and I rise 1, run 1, bing, there's my point, draw the line. Is that okay? Okay, so what I'm going to do here is I'm just going to change this just ever so slightly. The reason I'm changing it is because I want to start focusing not on the letters that we choose, but where they are in the equation. Okay? And I'm choosing A, I'm leaving C where it is because it's going to have meaning for us down the track. Okay? So I'm just changing the M for an A, and I'm not changing the C at all. So is that okay? So the A is still the coefficient of X, it's still the gradient, just giving it a different letter. The C is still the C, the constant. Okay. Rightio, so here's what I want to do. So you'll notice if you look down a bit further, oh, look at that graph. There's your Y equals X graph. You could have cheated if you'd scrolled a little bit, but that's okay. Today's learning number 1, right? You need to remember that Y equals X looks like that. Not a hard thing to remember, but you need to remember that, okay? Because we are going to be doing things where we start with what we call our basic function, which in this case is Y equals X. It's the simplest possible linear equation. Okay, Y equals X is the simplest possible linear equation where every component has a value, okay? And then we are going to play with it. And this is what you're going to do now. So on your OneNote, you will see a link that says linear function transformations. Could you please click on that link? Okay, doink. It will open up Desmos. That's cool too. The only problem in OneNote is you may not be able to see all the bits. So that's why I use click the link. But yes, you can do it in the OneNote, but sometimes it's not big enough. Okay, so what you will hopefully notice is that I've created a little equation with the same variables that we just talked about, the A and the C. Okay? So I'm just going to go back to my OneNote. You leave your graph up. I'm just going to go back to here. Here's the questions and now below that are the questions that I want you to answer. So you're going to play with the sliders. Now we've done this before a little bit, so I want you just to drag the sliders around. Okay, I want you to tell me, well, what is A? Like where is it in the equation? Now we've literally already answered that question. So what is A? It is the what? Coefficient of X. Okay, yes, it is the gradient in this context, but I want us to be a little bit more general than that, okay? So in this case, what is A? A is the coefficient of X, okay? And we're talking about a linear function, so the highest power of X is going to be X to the power of 1. So it's going to be our coefficient of that term, okay? It's the coefficient of X. Your job will be to, what does A do to the graph? So I want you to play around with A, explore different values of A and what's happening with the graph. Now, we already know the answer to this. What is A? Someone said, yeah, it was you, wasn't it? Yeah. What's A? The gradient, right? So we know that A impacts the gradient. What I want you to do is be a little more specific. So for what values of A, and we already know the answers to this too. When A is 0, what happens? When A is positive, what happens? When A is negative, what happens? Okay, play around with A. Then put A back to 1, because at the moment the defaults are A is 1 and C is 0. So Y equals X function. So once you've played with A and you've worked out what you think you're going to write, put A back to 1 and then play with C. Tell me what you see. S-E-E, not letter. Okay, and again, back into OneNote, just, so what is C? I won't answer that one out loud yet. What is C in the equation, right? And what does it do to the graph? So when you play around with C, what happens? Okay, so I'll give you about 5 minutes to play with that. Talk to each other about it while you're doing it, so you can come up with some sort of solution to those questions. How about A? Well, let's do C first, because I think C is the easiest. So what did we end up calling C? Isabel, the what?
The constant.
The constant, not the consonant. Okay, so it's the constant. What does the word constant in mathematics mean? Well, yeah, in mathematics, no variable. There's no variable attached to it. It doesn't change its value, hence the word constant. Okay, in our context, in this particular type of equation, what else is it? What else is C? It's the y-intercept. Okay, so I specifically wanted you to identify that it's the constant, okay, but it's also in this context the y-intercept. Okay, so when we explore C, what does changing C in a positive direction do to the graph? It changes the y-intercept. In which direction does it go though? Up. No, when C is positive. So if I move C in the positive direction, the y-intercept goes up. And how far does it go? So for example, if I make C into 2, what does that make my y-intercept? So where does it start? So where's it starting there? 0. If I want C to be 2, how far does it go? 2. Yeah, so it moves, whatever the value of C is how far it moves. Now, you're probably sitting there going, yeah, duh, right? But when we come to other types of functions a little bit later on, we can describe the way it moves, but how far it goes may not be exactly that number. It might be some relationship that we need to identify. So that's why I want us to be specific now. With the easy one, if I move it +2, it moves up 2 units. If I go -2, it goes down 2 units. So the sign of C determines the direction, the value of C determines how far. Does that make sense? Yeah? So, and again, you're probably sitting there going, yeah, okay, that's good, thank you, sir. Can we do this at every level? Because this is easy, right? So, if C is greater than 0, we go up. If C is less than 0, we go down. Now, we're going to use better terminology shortly, all right? But for the moment, does that make sense? Is everyone okay with that? Yeah? Okay. Let's go to A. So I've got C back. So what happens when I make A, well, what happens when I make A 0? It just goes horizontal, doesn't it? Okay, what does my equation become? Y equals what? No? Oh, it is at the moment, but if I do that, so what if I make A 0, what's the only thing left? The constant. So it's just whatever C is. And you can see we talked about this last term. Horizontal lines, 0 gradient. Okay, so back to 0. So A equals 0 is a bit pointless because it doesn't do anything. All right? So let's try positive. So what happens when A is positive? What does it do? Yes, it's got a positive slope, correct? So it's got a positive slope, and what else does it do? As A increases, what happens to the graph?
Does it go more up?
Goes more vertical, or it increases what? Gradient, or the steepness, doesn't it? Yeah? What happens when A is negative?
Increases.
It goes, but it sort of increases negatively, doesn't it? It sort of increases in a negative direction. Okay, now once again, that's a key understanding. Okay, so when A is greater than 0, okay, we have a positive, it's positive, quite obviously, and as A increases, gradient increases. Okay, when A is less than 0, whoops, it's negative. But the same thing applies. As A gets bigger negatively, the gradient just gets bigger negatively. Okay? And so what we're describing here is how those changes affect my basic graph. So I start with y equals x, and then I can manipulate it to form the linear function I want. Now, we don't necessarily do that with this type of function, but I'm just introducing something that you are somewhat familiar with. Okay? So let's do, now what I'm going to do today is introduce you to some terms. And these are the 3 terms that we are going to use. Okay? Dilation, translation, and reflection. Okay? So we're going to start using those terms. Now, Sophie said before to me, well, what's dilation mean? I said, well, you actually probably know. And she said, well, it gets bigger. And that's exactly what dilation does. So if something is dilating, it's getting bigger. Now, we can also get a negative dilation, or we can get A getting smaller, but we use the term dilation to indicate that sort of change. Okay? So a dilation in mathematics is a change in size, or more specifically in most of our contexts, a change in gradient. So we're going to change the gradient of the line. Okay? Is that all right? Make sense? So which of our two variables that we've investigated so far affect dilation? A. Yep, so when we play around with A, we're changing the gradient. We're changing the size of the line, the slope of the line. Okay? So whenever we talk about dilation, most of the time we're going to be talking about how A changes it. We'll see if that holds for the other functions, but let's go with there. All right, what does the word translation mean? This is a new one. Yeah. So back in middle school, grade 7 or 8, you would have done it. You would have done translations where you get a shape and you move it around the page. Yeah? So back in grade 7, you would have done, I think it was grade 7. Yeah, it was. Grade 7, you've done translations. Now, what were the two types of translations you can do? No, that's something different again. So flips a reflection. So this, what would we call this kind of sliding? Horizontal. What do we call this one? Vertical, right? So we have two types of translations. We can horizontally translate or we can vertically translate. Okay, now, with the variables that we've identified so far, we've only had two to start with. We had A and C. We've already identified that A has something to do with dilation. Which way did C move it? Horizontally or vertically? Vertically, didn't it? Moved it up or down, didn't it? So C is a vertical translation. In other words, we're just moving the graph up or down depending on what value C is. Okay? So with translations, we've got vertical or horizontal. Okay, and back in middle school, you called that a slide. Okay? We had flips, we had slides, and we had turns, if you recall. Okay? We don't have turns because we're not looking at rotational symmetry or rotation in this case. Not yet. You will next year, but not yet. Okay, so we're not doing the turns, but we are doing flips and slides. So this is the slide. Okay, we can slide horizontally and we can slide vertically. And so far we've identified that our C, okay, in that context is a vertical translation. What do you think reflection means? Mirror. Yeah, exactly. It's a mirror across. So it looked one way, it looks one, and the reflection, it looks across the other. So it looks exactly the same. Now the reflection, we have two ways that we can do that. We can reflect across the x-axis, or we can reflect across the y-axis. Now, in our context, we're only going to deal with x-axis reflections. We're not going to do y-axis reflections. Okay? Again, next year. We're just going to keep this simple this year. All right? So we're going to be looking at those types of transformations. Okay? And we're going to investigate and see, well, how do they affect? And the way we're going to do that is that we are going to look at transformations of parabolas. So we're going to start to investigate what does a parabola look like. So again, we're going to follow the same process. So this is the most basic kind of quadratic. Y equals x squared. It's got all the components that you need, has an x squared term. What would it look like on a Cartesian plane? So if you were to graph this on a Cartesian plane, what does it look like? Y equals x squared. What kind of graph is it? Parabola? Right, so what are the two ways we can draw a parabola? Minimum or a maximum. Right, so which one do we reckon it is? Minimum or maximum? Maximum would be this way. Minimum would be this way. What's the most common way that we've drawn them most of the time? We only draw them this way, don't we? Whenever we draw a parabola on the board, the majority of the ones that we've drawn so far have gone that way. Are they not? So that's what this one is. Okay, so it's going to be a minimum. Where's my intercept? Where's my turning point going to be? Any ideas? Where do you think the most basic possible parabola, where's it's going to be? The origin. Yep, both of you. So the turning point's at the origin. That's the most basic type there is. Okay? And so we're going to draw our parabola. Okay? And that's it. That's y equals x squared through the origin. So we're going to label that point because it's such a key piece of information. Okay? Whenever we're identifying parabolas, we need to identify three key pieces of information. X-intercept, y-intercept, turning point. In this case, they're all at the same place. Okay? So once again, that is our first piece of information that we need to recall. What does y equals x squared look like? That. Cool? Okay. A couple of weeks ago, it probably was a couple of weeks ago now, I hardly ever see you guys anymore. A couple of weeks ago, I talked to you about the two different forms that quadratics can take. And we focused on the ax squared plus bx plus c. There is another form, which we call the turning point form. For very obvious reasons, which some of you have already discovered. But that's it there. Okay? The two dots, why I've got two dots, I have absolutely no idea. So I'll get rid of it. I don't know why. Okay? So this is the turning point form of quadratic. What form is that? How did we get to that point? What process did we do with our quadratic to get to look like that? Completed the square. Right, so we got a quadratic, we completed the square, we got to that. Right? I'm not going to ask you to complete the square today. That's already way too much thinking for most of you who are struggling to stay awake. Okay? So, just like we did last time, we're going to investigate some variables. Okay? Now, if we recall, what did A represent on our linear equation? Coefficient, and what did it do? It changed the steepness, it changed the slope, didn't it? Alright? We don't have a C, because C represented the y-intercept. Okay, so I've deliberately got different letters because I don't want us to get confused. So now I've got a H and a K. Why H and K? Why not? Okay, literally that's the answer. Why not? It's not B, it's not C. Okay, so H and K. That's very commonly used. So, here's another link that I'd like you to open. Could you please go into that link and follow the same processes? So you'll notice that here's our basic y equals x squared graph. Right? Over here are our default values. A is 1, H is 0, K is 0. In any order you want, explore those three letters. What does A do? What does H do? What does K do? Yep. Try and use the new terminology. So try and use things like dilation, translation, vertical or horizontal, or both, or whatever, and then reflection as well. Try and use those terms. What do they do? Alright? Now below the graph in OneNote, I've got A, H and K as letters. There's somewhere for you to jot down your notes. Give you a few minutes to do that.
Tell me what you know about the scale. Ladies, shh. Can you tell me what you scored about A, please? Okay, so when does it reflect?
Doesn't it always reflect?
No. So let me put these back to the default. There we go. Yes. So, when we start with our basic function, remember we always start, can you get it there? We always start with y equals x squared. So we're always going to be transforming y equals x squared. So at the moment, y equals x squared, A is what value right now? What is the value for A right now? Not what I've got, but what should it be? 1. Right? It should be 1. Right, there, 1. Okay, so that's our default value. A equals 1. So if I go up from 1, right, what happens to the graph? What do you mean by smaller? It's a dilation. Because what is happening to the arms of the graph? They're getting closer, aren't they? So if you want to think about that, each of the arms are getting steeper. So we're changing the gradient, which is what happened for the linear function as well. Right? So when A is greater than 1, we get a dilation towards, so the arms are going towards what? The y-axis, exactly right. So the arms are dilating towards the y-axis. That's when A is greater than 1. Okay? What did you discover when A was between 0 and 1? No, between 0 and 1. So like a half, or 0.4, or 0.9. It's going wider, isn't it? It's getting wider. So it's dilating away from the y-axis. Right? So it's getting steeper. When it's greater than 1, it's getting flatter. When it's a fraction between 0 and 1. And if you're not sure about this, just play with your slider and have a look. Try different values in those ranges. When A equals 0, it's a pointless graph. Right? So we're not even going to worry about what happens when A is 0 because it's not a quadratic anymore. So we don't care. What happened when A was less than 0 though? So when A was negative, what happened to the graph? It reflects across the what? X-axis, exactly right. Bless you. I can still bless you, can I not? Okay, fine, I'll take it back. No, Gonski. Alright. So, when it's less than 0, in other words, it's negative, that's the reflection across the x-axis. Now, think about the linear function we did a bit earlier. When the gradient is negative, it starts like this. When it's positive, it starts like this. When it becomes negative, it's down there now. So in fact, it's exactly the same change. It's reflecting across the x-axis. So it's the same transformation, doesn't matter what kind of graph it is. We get a reflection if it's negative. Okay? So that's our A values. Is that okay with everyone? Right here, what did H do? Horizontal translation. Which direction? So, okay, so to the right when what? Okay, so H is a horizontal translation. So the graph slides left to right, yes? When we move H just goes back and forth this way, right? When H is greater than 0, which way do we go? To the right. Yep, so when H is greater than 0, we go to the right. When H is less than 0, we go to the left. Pretty easy. Okay? Last one, K. What did it do?
Vertical translation.
Yes. Yes, it's a vertical translation. Okay? When K was greater than 0, which way did we go? Up. Exactly the same as what happened with C in the type, but not the value. And when K less than 0, we go down. Now, did anyone else notice anything interesting about H and K? Yes, they are, but in terms of their values. Let me go back to the graph. Let me make H, and let's just change this a little bit. Let's make H 2. Right, so that means I've translated 2 to the right. And let's make K 3. So I made H2 and I've made K3. Do we notice anything significant about my graph now?
They have a relationship.
Yes? What?
They have a relationship.
Yes, they do. What is the relationship between h and k and some aspect of my graph now? Yes, it did. The y-intercept is now 7. So not really any link there. What else has changed? Oh, the turning point. Oh, what are the coordinates of the turning point? 2, 3. Do those numbers sound familiar? Yes? Is 2, 3 any number on the board that we've got already? H and K. Oh, okay. What if I made H negative 5 and I made K 4? Any significance between those two and anything on the graph? No, really? No? So what does that make H and K? Coordinates of the turning point. Hence the reason it's called the turning point form. OMG, mind blown. Right? We math people aren't stupid all the time. Most, yes or no, right? So, we go back to our form, y equals a, x minus h squared plus k. It's called our turning point form. We know what each of the letters do individually. A has a relationship with dilations and reflections. H is our horizontal translation. H for horizontal, nice easy way to remember it. K is our vertical translation. No real easy way to remember that because there's no V in vertical in K. Right? Vertical, but if you can't spell, it might be a way to remember it. Okay? But what is significant is the coordinates that H and K are our turning point. So if we complete the square, right? If we complete the square and identify our H and our K, that gives us our turning point. What is significant about that? We'll look at some practical examples next week, because this is our last lesson this week, and we'll see, well, so what? What's that useful for? It has uses, we're going to get there. So let's do some examples. So let's have a look at 3 different graphs. Okay, so here's the sketch and graphs of the following quadratic relations, labelling the turning point and the y-intercepts. We're just going to worry about the y-intercepts, we're not going to worry about the x-intercepts at the moment. So the first one is y equals 3x squared. So underneath each of the Cartesian planes, so we'll do Cartesian plane A first. So we'll do this one first. So y equals 3x squared. Forgot to label my axes. Okay. So the first thing we're going to do, underneath the graph, could you identify for y equals 3x squared, what is A, what is H, what is K? Okay, so for that graph, what is A, what is H, and what is K? So y equals 3x squared. So think about what I'll do up here is I'll write up the general form. That's the general form, so that's where each of those letters appear in the equation. What is A, what is H, what is K? Out of charge?
Yep.
Do you have your charger here?
No.
Is it in your locker? Is it at home?
Yes.
Oh, it's a start. Okay, so right, so you got paper and pen? Okay. What is A? 3? Carlos is putting forward 3, is he right? Yep. Coefficient of x squared. What's H? 0. What's K? 0. So the way we draw these is this. Oh. What do you mean how? Okay. What's my turning point for this graph? Y equals 3x squared. The origin. Okay, it's 0, 0. A is 3. So let's think about how we draw these first. So this is the habit I want you to get into. On your Cartesian plane, could you please draw for me the basic quadratic function y equals x squared? Okay, so y equals x squared is where we're going to start this graph. Okay, so there's my y equals x squared. It's just a sketch. That's all I want you to do. Now, relative to that graph,
draw for me what 3x squared would look like. Yes, that's exactly right. So with a different colour pen or a different choice on your laptop, draw for me 3x squared. So we know what 3 is. A is the dilation. Remember, when it's greater than 1, what happens to the graph? It goes in, gets skinnier. So you're just going to draw a graph that does this, because we haven't changed our turning point. It's still at 0, 0. And there's my y equals 3x squared. Okay, I've labelled both of my graphs, so I know which is which. Does that make sense? Okay. On the other two graphs, so other two Cartesian planes, could you please draw y equals x squared? So just draw them in. The reason they are there is because it gives us a starting point. It gives us something to judge against. Okay? So there's my y equals x squared. Just label those so we know which graph is what. Y equals x squared. Just like that. Okay, so graph number B is, I'll write it down the bottom here now, y equals negative x squared plus 4. Okay, that's my next graph. What did we do first last time? Found A, H and K. So underneath there, could you write down what is A, what is H, what is K? If we can get into these habits now, this makes this set of work so much easier. Okay? What is A, what is H, what is K? For this example. Okay, Pierre, what do you reckon A is? What do you reckon A is? Not 0. If A is 0, we don't have a quadratic. So A will never ever be 0. 2 seconds. So where does A appear? A is at the front. So what's at the front here? Negative what? Negative 1. Okay? So A is negative 1. Katie, what's H, do you think? 0 is correct. H is 0. What's K? 4. We'll get, because we'll look at it compared to the next one. That'll make it easier to explain, okay? So, all right, do you notice the difference between the two? Yeah? So notice here it's just x squared, whereas this one's got x minus 2 all squared. So if you look at the format, there's no constant inside, there's no number inside the brackets. So that means H is 0. Okay? So where's my turning point now? For this graph, for number 2. Where's my turning point? 0, 4. Because my turning point is HK. Right? So HK is my turning point, so that's at the point 0, 4. So that's going to be up there somewhere. Right? That's 0, 4. Because there's no horizontal translation and a 4-unit up translation. That's it. And what are we moving? We're moving my turning point. It's my turning point that moves. Okay, what does the negative A mean? It's going to be a maximum. So it's going to reflect. So instead of being a U shape, it's going to be a frowny face or a mountain. Right? So it's going to go, ooh. And I need to make sure, as best I can, that it's the same shape as the other one, because I haven't dilated it, because the dilation's 1. So it's the same shape, it's just reflected. So it looks like that. Have a go at the last one yourself. Okay, have a go at the last one yourself. Well, what's A, what's H, what's K? Put on your turning point. Are there any reflections or dilations? What is it going to look like? Bye. Yes.
coefficient. Oh no, because 4's...
This 4 you mean?
Yeah.
So that 4 means, so A, B and C, so H and K are your turning point. So it's going to be at 0, 4, so it's going to be up there somewhere. Oops.
And then when A's...
Negative, it flips it over. Yep, that's exactly right. Yep. So remember, we're moving our turning point. So our turning point exists at the moment at 0, 0. Where's it going to go to? And then how else does the graph change, if at all? Who said to square anything? Yep, no, it's not. Squared's part of the form of the function. We just got to identify the 3 letters that are involved: A, H, and K. See how this, which is again the example I'm going to do in a second. But notice how this is x minus h. So what is the value for h to make that x minus 2? So the minus sign is already there. So h has to be 2. Okay? Which brings me to my last example, which I'm about to write up. There is an answer, it's 1, yes. If A can never be 0.
Yeah, sorry.
If there's no number, it's assumed to be 1, yes. Just tucked another one in there, yeah. We haven't finished each of those questions because there's some we haven't done yet, but we'll go back to them in a minute. All I want to do at the moment is just get our graphs right. So, A, H and K are 1, 2 and 0, which means my turning point is at 2, 0, so it's a horizontal translation only, nothing else has happened, right? And then we've got no other change in form. There's no reflections, it's the same size, there's no dilations, so it's roughly the same shape, just slid across. Is that okay? Welcome back, Carlos.
Draw thing. Can you just draw it like randomly?
So we'll see how that has to go that way though, because H is positive too. If you look at the general form, wherever it is, so you haven't got it, okay. So the general form is y equals A times x minus H. So the minus is already there, which means H is positive.
Oh.
Compared to what we're about to do here. See, notice here that I've got a plus sign. The general form was x minus. So if I make that a minus, what does that make that number? A negative 4. So therefore H is negative 4. Does that make sense? Yep. Okay, last example. Notice it's got a plus 4. So first of all, I'm assuming that most of you have realised that A is 2 and K is negative 1. Reasonable? Yep. Okay, so let's look at what's going on inside the brackets. Okay, so our general form inside the brackets says x minus h all squared. Right? But I've got plus 4. So how do I write that as x minus something? So what's the h going to have to equal to make it x minus something be the same as x plus 4? Negative 4. So my h has to be a negative number. So h is -4. Okay, because I need the 2, in order to be x plus, my general form has a minus sign, so I need them to cancel out. Once I've done that, I can then, whoops, I haven't got my general form there. Where are you? And I get that. Yeah, it should be narrower. Okay. We're going to pause there for a moment. Pretty warm day today, and most of you look like you're about to fall asleep.
Yes.
So, well, this is what I propose. So, I want to just summarise what we've done so far, and then I'll give you some questions to do, and we'll just ease our way into the day. Okay? So, let's just quickly summarise. So, what we've tried to do today is, and we're going to be doing this across a lot of different types of graphs. Slowly, not like today. Today was quick, because we've already got a good understanding of what a parabola does, what it is, how it works. Okay? So what we've tried to do is identify, first of all, what the general form of a quadratic is in terms of its turning point, and then what the relationships are between the letters in their different positions and how they affect the graph. Okay? Once we identify that A dilates and reflects, H does a horizontal transformation, and K does a vertical transformation. Once we identify what we're moving, so we pick the turning point, we move that. Because the turning point is the easiest point in a quadratic to find. Everyone, if I draw a quadratic, can find the turning point. You just go, boom, there it is. Right, literally. So you go, boom, there it is. Okay, and then you move it, and then everything just drags along with it. Okay, so when we talk about translations, yes, we're translating the whole graph. Yes, we're affecting the whole graph, right? But when we want to sketch it, we've got to find a point that we can focus on and move that one. Then everything else follows along. Okay? Now, we have done some examples of some sketches. What we are going to do next week is say, okay, some little extra things like, how do I find the intercepts? So, for example, on the last question, how many x-intercepts do you expect to find on this graph? 2. How do you know? Can you see 2? Yeah. Okay. Now, there's my equation. How would I find the x-intercepts, ladies and gentlemen? Let y equal 0. Now, have we done equations like this, where we've let y equal 0 and rearranged it? Yes, of course we have. So we could do that. And we could find those 2 values if we wanted to, or needed to. How do I find the y-intercept? Let x equal 0. We can do that one in our head. Let's do that. What is my y-intercept going to be? So put 0 in for x and solve it. What are you going to get? Do it in your head. Good mathematical practice. I know. So look, 0 plus 4 is 4. 4 squared, 16 twos, take away 1, 31. So, does that look reasonable given my graph? Is it quite high up the y-axis? Yeah? So my graph looks reasonable. So we can find x and y intercept with the equation reasonably easily. Well, we've done practice of that already. That's where we're going next week. Okay? And then we're going to look at questions like this one. We're not going to solve this now, but I want you to have a look at it. Okay, I'll try and make it a bit bigger for those people with eyesight like mine and can't see 2 inches past your nose. The equation for an arch, in particular bridge, is given by that equation, where h is the height above the base of the bridge and x is the distance from the left-hand side. So it's a bridge like a parabola. How do I know it goes this way? Apart from it's a bridge, and not many bridges do that. How do I know from my math, from the equation, that the parabola does that? What is it in there that tells me it does that? Non-negative gradient, but you're so close. Which variable affects reflection? A. What's A in this example? Negative 1 on 500. The negative part is the reflection. So normally a parabola sits upright, right? This one goes that way because of that negative sign. There's a little bit of information. It makes sense, right? What's the turning point of the graph? So it's going negative 100 means which way have we moved the turning point? 100 units to the left, or right, sorry. My left, your right. And how far up? 20. So the maximum height of the bridge is 100 metres along and 20 metres high. And so on. We're going to look at examples, it's not my mum put a phone, of that type, where we can look at a function and go, oh, you can solve that reasonably easily. That's where we're going next week. Okay? For today, for the rest of today, what I would like you to do, in a gentle way to finish the lesson off, all right, is this is exercise 7b. Question 1 says, here's some equations, what's the turning point? So what's h and k? This one says, if you make this transformation, what do you see? Okay, so you're writing literally one word. So here you're writing 2 numbers and a couple of brackets. Over there you're writing a word. That is where we will leave today for you to practice those things. Okay? Because it's been a long day. But don't pack up. I will leave that on the screen for those whose laptops have died.